The morning of August 9th, 1943, in the jungles outside Munda Point on New Georgia Island, Japanese engineers gathered around something they had been hunting for months. An American M4 Sherman tank sat silent and still, its metal hull bearing scars from battle but otherwise intact. This wasn't just another piece of captured equipment. This was the machine that had been terrorizing Japanese positions for weeks, appearing seemingly immune to the tropical heat that had turned their own tanks into suffocating metal coffins. Lieutenant Takeshi Yamamoto, chief engineer of the Japanese Sixth Tank Regiment's Technical Evaluation Unit, approached the Sherman with the careful reverence of a man examining a puzzle he desperately needed to solve. Around him, his team of 7 engineers carried notebooks, measuring tools, and cameras. Their orders were explicit and came directly from Imperial General Headquarters in Tokyo. Find out why American tanks could operate continuously in challenging conditions that incapacitated Japanese armor within hours. The answer, they would discover, lay not in some secret weapon or advanced technology, but in a design philosophy so fundamentally different from their own that it would force a complete reassessment of Japanese tank engineering. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The story of this captured Sherman and what Japanese engineers discovered beneath its hull represents more than a technical tale. It illuminates the vast philosophical divide between American and Japanese military engineering, a divide that extended far beyond tanks to shape the entire course of the Pacific War. Japanese tank design in 1943 remained rooted in principles established in the 1920s and early 1930s. Their Type 97 Chaiha medium tank, the most common Japanese tank in the Pacific, had been designed with different priorities than its American counterparts. Weight restrictions dominated Japanese tank design philosophy. Japan's bridges, particularly in Manchuria, where tanks were expected to operate, could not support heavy vehicles. Japanese doctrine emphasized speed and maneuverability over armor protection. The result was tanks that weighed between 14 and 15 tons, far lighter than the 30-ton Sherman. This weight consciousness extended to every component, including the cooling system. The Type 97 Chaiha used an air-cooled diesel engine, the Mitsubishi Type 97 producing 170 horsepower. Japanese engineers had chosen air cooling deliberately, believing it simplified maintenance and reduced weight. Liquid cooling systems, they reasoned, added complexity, weight, and vulnerability. A single bullet puncturing a radiator could disable a tank. Air cooling eliminated this weakness. In the moderate climate of Manchuria, where Japanese tanks had been tested extensively during border conflicts with Soviet forces, this design philosophy seemed vindicated. The Type 97 performed adequately in temperatures ranging from -30 degrees Celsius in winter to +30 degrees Celsius in summer. The air cooling system, combined with ventilation fans and crew hatches, maintained tolerable internal temperatures. Japanese tank crews, selected for their ability to endure harsh conditions and trained to view physical discomfort as character building, adapted to the cramped, hot conditions inside their vehicles. When Japanese forces deployed to the South Pacific beginning in 1942, these design assumptions began to fail catastrophically. The tropical environment of islands like Guadalcanal, New Georgia, and Bougainville presented conditions far beyond anything Japanese tanks had been designed to handle. Ambient temperatures regularly exceeded 35 degrees Celsius. Humidity approached 100%. Dense jungle vegetation blocked airflow. Most critically, combat operations required tanks to operate continuously for hours, their engines generating tremendous heat that air cooling systems could not dissipate effectively. Japanese tank crews began reporting serious problems within weeks of deploying to the tropics. Internal temperatures inside Type 97 tanks exceeded 60 degrees Celsius during extended operations. Crews suffered heat exhaustion and heat stroke. Ammunition stored inside the tank became dangerously hot to touch. Engine performance degraded as components overheated. Lubricating oil thinned beyond effective viscosity. Most seriously, tanks frequently had to cease operations and shut down their engines to cool, leaving them vulnerable and reducing their tactical effectiveness. Lieutenant Yamamoto had documented these problems extensively. His reports to Imperial General Headquarters detailed instances of Japanese tanks being forced to withdraw from combat not due to enemy action, but because crews could no longer function in the heat. He had measured internal tank temperatures during operations, recording readings that exceeded safe limits for both men and machines. He had interviewed dozens of tank crews, hearing consistent accounts of debilitating heat that made extended combat operations impossible. What baffled Yamamoto and his fellow engineers was that American tanks appeared immune to these problems. Intelligence reports and prisoner interrogations indicated that Sherman tanks operated continuously for 8, 10, sometimes 12 hours without heat-related failures. American tank crews, supposedly soft and dependent on material comforts according to Japanese propaganda, somehow endured conditions that incapacitated hardened Japanese tankers. This contradiction demanded explanation. The Sherman tank that Yamamoto's team had captured provided the opportunity for direct examination. The tank had been disabled not by overheating, but by a lucky hit from a Type 92 heavy machine gun that had damaged its tracks. The crew had abandoned the vehicle after it became immobilized, leaving it largely intact. Japanese infantry had secured the area, and Yamamoto's technical team had been rushed forward to examine this prize before American forces could recover or destroy it. Yamamoto's first observations, recorded in his notebook and later translated by Allied intelligence after the war, revealed his systematic approach. He noted the Sherman's weight, approximately 30 tons, more than twice the Type 97's 14 tons. He measured the armor thickness, 76 mm on the front hull compared to 25 mm on Japanese tanks. He examined the main gun, a 75 mm M3 that was significantly more powerful than the Japanese 47 mm Type 1. These observations confirmed what Japanese intelligence already knew. American tanks were heavier, better armored, and more heavily armed. But none of this explained their heat tolerance. The breakthrough came when Yamamoto and his team began examining the Sherman's engine compartment. Unlike Japanese tanks with their air-cooled engines, the Sherman used a liquid-cooled system, the Continental R975 radial engine, producing 400 horsepower, nearly 2.5 times the power of Japanese tank engines, was surrounded by a sophisticated cooling system that Japanese engineers had never seen implemented at this scale. The system's complexity astonished Yamamoto's team. A large radiator, positioned at the rear of the tank, contained multiple rows of cooling tubes. Coolant fluid, a mixture of water and ethylene glycol, circulated through the engine block, absorbing heat, then flowed to the radiator, where air passing through the tubes dissipated that heat. 2 large cooling fans, mechanically driven by the engine, pulled air through the radiator at high volume. The entire system was designed with redundancy. Multiple coolant passages ensured that blockage in one area would not cause catastrophic failure. The radiator's size provided cooling capacity far beyond minimum requirements. Temperature sensors and pressure relief valves protected against overheating. Yamamoto's notes, preserved in captured documents, reveal his growing realization of what he was seeing. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The American tank had been designed from the beginning to operate in any climate, from Arctic cold to tropical heat. The cooling system wasn't an afterthought or a component minimized to save weight. It was a primary design consideration, engineered with the same care and sophistication as the armor and weapons. Japanese tank design philosophy had treated cooling as a secondary concern. Weight, restrictions, and the desire for mechanical simplicity had led to minimalist cooling solutions. The assumption had been that crew endurance and proper tactical employment could compensate for limited cooling capacity. The Sherman represented the opposite philosophy. Rather than expecting crews to endure excessive heat, American designers had engineered the tank to maintain tolerable conditions regardless of external environment. This wasn't about making tanks comfortable for soft American soldiers, as Japanese propaganda suggested. It was about maintaining combat effectiveness over extended periods. What Yamamoto discovered as he examined the Sherman more closely was that the cooling system integrated with virtually every other aspect of the tank's design. The ventilation system that provided fresh air to the crew also drew heat away from the engine compartment. The ammunition storage areas were positioned away from the hottest zones. The engine compartment itself was separated from the crew compartment by insulated barriers that reduced heat transfer. The sophistication extended to details that Japanese engineers had never considered important. The coolant fluid itself was engineered to specific properties. Its boiling point exceeded 120 degrees Celsius, allowing the system to operate at higher temperatures without vapor lock. Anti-corrosion additives prevented the accumulation of deposits that would reduce cooling efficiency. The mixture ratio could be adjusted for different climates. The radiator design incorporated lessons from automotive engineering that Japanese tank designers, working largely in isolation from civilian industry, had not implemented. The tubes were arranged to maximize surface area while minimizing air resistance. The fin spacing optimized heat transfer. The entire assembly was designed for field maintenance, with drain plugs, accessible connections, and replaceable components. Yamamoto's team spent 3 days examining the Sherman before American artillery forced them to abandon the site. During those 3 days, they photographed every detail, measured every component, and recorded extensive notes. They attempted to remove the radiator for transport back to their base, but the size and weight made this impossible under combat conditions. Instead, they sketched detailed diagrams and took measurements that would allow reconstruction. The implications of what they had discovered began to dawn on Yamamoto as his team prepared their report. The cooling system was not just about preventing overheating, it was about sustained operational capability. An air-cooled Japanese tank might operate for 2 hours before heat forced a shutdown for cooling. A liquid-cooled Sherman could operate for 8 hours or more, providing 4 times the tactical availability. In a sustained engagement, this difference was decisive. Japanese tanks would have to rotate out of combat to cool, while Sherman tanks remained continuously engaged. The productivity ratio, as Yamamoto calculated it, meant that one Sherman provided the sustained combat power of 3 or 4 Japanese tanks. This wasn't about individual component superiority, it was about system-level design philosophy. American engineers had understood that a tank's effectiveness depended not just on its armor and weapons, but on its ability to remain operational. They had invested weight, complexity, and manufacturing resources into ensuring continuous operation. Japanese engineers, constrained by weight limits and focused on traditional combat characteristics, had created tanks that were tactically mobile but operationally limited. The captured Sherman forced Yamamoto to confront a question that had profound implications beyond tank design. If American engineering philosophy so thoroughly exceeded Japanese approaches in something as fundamental as cooling systems, what did that suggest about the broader industrial and technological competition? The answer, which Yamamoto privately acknowledged in his diary, though he could not state openly in official reports, was deeply troubling. The technical report that Yamamoto's team submitted to Imperial General Headquarters in September 1943 was a meticulous document of 47 pages, including detailed drawings and measurements. The report, captured after the war and translated by Allied intelligence, reveals both the thoroughness of Japanese analysis and the institutional resistance to its implications. Yamamoto's report documented every aspect of the Sherman's cooling system with engineering precision. Flow rates of coolant fluid measured in liters per minute, radiator surface area calculated in square centimeters, fan airflow volumes estimated from blade dimensions and rotation speed, temperature gradients across the cooling system inferred from component wear patterns. The level of detail demonstrated that Japanese engineers understood exactly what they were looking at. The report's conclusions were carefully worded but unmistakable. American liquid cooling systems provided superior performance in tropical conditions. The weight penalty, approximately 800 kilograms for the complete cooling system, was justified by the operational advantages. Japanese air-cooled designs could not match American operational endurance in high-temperature environments. The report recommended immediate development of liquid-cooled engines for future Japanese tank designs. The response from Imperial General Headquarters, preserved in archives, was bureaucratically cautious. The technical findings were acknowledged. The superior performance of American cooling systems was accepted, but the recommendation for fundamental redesign was deflected. Japan's industrial capacity, already strained by the demands of naval construction and aircraft production, could not support a complete redesign of tank production. Existing factories were tooled for air-cooled engines. The steel required for radiators was needed for ships and aircraft. Training mechanics to maintain liquid cooling systems would take months. Most fundamentally, the weight increase required by liquid cooling systems would necessitate redesigning bridges and transport ships throughout Japan's defensive perimeter. The institutional inertia was too great. Japanese tank design would continue along established paths. Yamamoto's report was filed and its recommendations noted, but no fundamental changes were implemented. The Japanese tank forces would continue to operate with air-cooled designs throughout the remainder of the war, accepting the operational limitations that Yamamoto had documented. For Yamamoto personally, the captured Sherman represented something beyond a technical puzzle. His diary, recovered after the war, reveals a man confronting uncomfortable truths about the conflict he was part of. He had been trained to believe in Japanese technological prowess and the superiority of Japanese engineering philosophy. The simplicity and efficiency of air cooling had seemed obviously superior to the complex and heavy liquid systems used by Western nations. The Sherman forced him to recognize that this belief was wrong. American engineers had not chosen liquid cooling because they were unwilling to accept the discipline of weight restrictions. They had chosen it because they understood that sustained operational capability mattered more than minimizing weight. They had the industrial capacity to build heavy tanks and the logistical capability to transport them. They had the organizational sophistication to train mechanics in complex maintenance procedures. Most fundamentally, they had a design philosophy that prioritized system-level effectiveness over component-level elegance. Yamamoto's diary entries from late 1943 reveal his growing pessimism about Japan's prospects in the war. If American superiority in something as seemingly mundane as tank cooling systems was this overwhelming, what did that suggest about the broader industrial competition? The answer, he privately acknowledged, was that Japan was fighting an opponent whose industrial and engineering capabilities exceeded their own by margins too large to overcome through fighting spirit or tactical cleverness alone. The story of the captured Sherman and its cooling system might seem like a narrow technical tale, but it illuminates something larger about the Pacific War. The conflict was not just about battles and strategies. It was about industrial philosophies, engineering approaches, and organizational capabilities. In every domain, from ship construction to aircraft production to tank design, American and Japanese approaches reflected fundamentally different assumptions about how to optimize military effectiveness. Japanese military culture emphasized simplicity, lightness, and the warrior spirit that could overcome material disadvantages. This philosophy had served them well in the 19th century and early 20th century, when wars were short and fought with relatively simple equipment. But by the 1940s, warfare had become an industrial endeavor where sustained operational capability and system-level design mattered more than elegant minimalism. American military culture, shaped by industrial experience and organizational sophistication, understood this shift. Tanks needed cooling systems that could sustain operations for entire days, not just individual battles. Ships needed damage control systems that could keep them fighting after hits. Aircraft needed redundant systems that could bring pilots home despite battle damage. These design philosophies reflected different assumptions about what won wars. The Japanese assumption was that superior spirit and tactical skill could overcome material disadvantages. The American assumption was that superior systems and sustained capability would eventually prevail regardless of individual tactical outcomes. The Sherman's cooling system, examined in a jungle clearing by Japanese engineers who were beginning to understand how outmatched they were, stood as a small but telling example of which philosophy would prove correct. Lieutenant Yamamoto survived the war, returning to Japan in 1945 after spending the final months of the conflict in a series of hospital posts far from the front lines. His technical expertise was too valuable to risk in combat. After Japan's surrender, he briefly worked with American occupation forces, helping to assess Japanese military technology and explaining the reports he had written during the war. In interviews conducted in 1946, Yamamoto spoke with remarkable candor about what the captured Sherman had revealed to him. He described the moment of understanding when he had first comprehended the sophistication of the American cooling system. He acknowledged that Japanese engineers had the theoretical knowledge to design similar systems but lacked the industrial capacity and organizational culture to implement them at scale. Most poignantly, he reflected on the broader implications of what he had discovered. The cooling system, he said, was not just a technical solution. It was a manifestation of American industrial philosophy. Americans built things to last, to work continuously, to be maintained in the field. Japanese built things to be light, simple, and elegant, assuming that skilled users could compensate for limitations. In a long war of industrial production, American philosophy would inevitably prevail. Yamamoto's post-war career took him into automotive engineering, where he helped rebuild Japan's civilian vehicle industry. The lessons he had learned from examining the Sherman influenced his work. Japanese automobiles of the 1950s and 60s would incorporate sophisticated cooling systems, reliable components, and design philosophies that prioritized sustained operation over minimal weight. In this way, the technical knowledge gained from that captured tank in the jungles of New Georgia contributed to Japan's post-war industrial success. The technical report Lieutenant Yamamoto submitted was not the only Japanese examination of captured American armor during the Pacific War. Between 1942 and 1945, Japanese forces captured or recovered fragments of dozens of American tanks. Each examination added pieces to a growing puzzle that Japanese military engineers struggled to comprehend. The pattern that emerged was not about individual components being superior, but about entire systems designed with a level of integration and sophistication that Japanese engineering culture had not anticipated. In November 1943, Japanese engineers at the Sagami Army Arsenal outside Tokyo received components from 3 different Sherman tanks recovered from battlefields across the Pacific. These pieces, shipped at great expense and difficulty given Japan's deteriorating supply lines, represented one of the Imperial Army's highest technical intelligence priorities. The engineers assigned to examine them included some of Japan's most experienced mechanical designers, men who had spent decades developing tanks, aircraft engines, and industrial machinery. What they discovered in their examination went far beyond cooling systems. The engine assembly from one Sherman revealed manufacturing techniques that Japanese factories could not replicate. Precision tolerances on piston rings measured to thousandths of an inch, bearing surfaces finished to smoothness levels requiring specialized grinding equipment, alloy compositions that balanced strength, weight, and heat resistance in ways Japanese metallurgy had not achieved. Each component reflected not just good engineering design, but advanced manufacturing capability. The cylinder head casting showed no visible porosity or defects. Internal passages for coolant and oil were smooth and precisely dimensioned. Threaded holes were cut cleanly with no rough edges. These details might seem insignificant individually, but collectively they indicated manufacturing quality control that exceeded Japanese industrial standards. One engineer, Hiroshi Nakamura, noted in his examination report that the engine components showed consistency across all 3 samples. Parts were interchangeable without hand-fitting or adjustment. This standardization meant that field repairs could be accomplished by simply swapping components, while Japanese tanks required skilled mechanics to hand-fit replacement parts to individual engines. The implications for maintenance and operational availability were profound. The transmission assembly proved equally revealing. American tanks used a synchromesh transmission that allowed smooth gear changes without requiring precise timing and double-clutching techniques. Japanese tank transmissions, derived from designs dating to the 1920s, required skilled operation and frequent adjustment. American tankers could change gears quickly and easily, even under combat stress. Japanese tankers needed extensive training to operate their transmissions effectively, and mechanical wear quickly made gear changes difficult and unreliable. The differential and final drive components showed engineering approaches fundamentally different from Japanese practice. Where Japanese designs minimized weight and used lighter materials stressed close to their limits, American components were robust and over-engineered. Gear teeth were larger than strictly necessary. Housings were thicker than minimum structural requirements. Bearings were sized with generous safety margins. This design philosophy meant American components lasted longer and tolerated abuse that would destroy Japanese equivalents. Japanese engineers understood the theoretical advantages of such robust design, but struggled to implement it within their industrial constraints. Japanese steel production, despite impressive growth in the 1930s, remained limited compared to American output. In 1943, Japan produced approximately 7 million tons of steel, compared to America's 80 million tons, more than an 11-fold difference. Every kilogram of steel used in a tank component was steel not available for ships, aircraft, or weapons. Weight minimization was not just a design preference, but an industrial necessity. The electrical systems in the captured Sherman components revealed another dimension of American engineering sophistication. The tank used a 24-volt electrical system, double the voltage of Japanese tanks. This allowed smaller, lighter wiring to carry the same power and provided more reliable starting in all conditions. The generator and voltage regulator showed sophisticated design with automatic controls that Japanese electrical systems lacked. The wiring harness itself demonstrated attention to detail that impressed Japanese engineers. Wires were color-coded for easy identification. Connections used standardized plugs that could be disconnected and reconnected quickly. The entire harness was protected by rubberized conduit that guarded against moisture, abrasion, and damage. Japanese tank wiring, by contrast, used minimal insulation and simple twisted connections that frequently failed in the humid tropical environment. The instruments and controls reflected a design philosophy focused on crew effectiveness. The Sherman's driver had clear, easy-to-read gauges for engine temperature, oil pressure, and fuel level. Warning lights indicated system problems. The layout was logical and consistent. Japanese tanks had minimal instrumentation, requiring drivers to judge engine condition by sound and feel, a skill that took extensive experience to develop and was unreliable under combat stress. Captain Kenji Watanabe, an experienced tank officer brought in to evaluate the captured components from an operational perspective, provided observations that complemented the engineer's technical analysis. His report, recovered from Japanese archives after the war, described how these design differences affected combat effectiveness in ways that technical specifications alone could not capture. Watanabe noted that the Sherman's ergonomics suggested a design process that included input from actual tank crews. The commander's position provided good visibility and easy access to controls. The gunner's station allowed comfortable operation of the main gun. The loader had adequate space to handle ammunition. Even the driver, working in the most confined space, had acceptable room to operate controls. Japanese tanks, Watanabe observed, felt like they had been designed by engineers who had never spent hours inside an operating tank. Controls were awkwardly positioned. Visibility was limited. Space was so cramped that crew members could barely move. These limitations were accepted as necessary sacrifices for weight reduction, but they directly impacted combat effectiveness. A cramped, uncomfortable crew tired quickly and made more mistakes. The cooling system that Yamamoto had first examined took on new significance in light of these broader observations. It was not an isolated example of American engineering superiority, but part of a comprehensive design philosophy. American engineers designed tanks to keep their crews effective over extended periods. Japanese engineers designed tanks to meet specifications for armor, armament, and mobility, expecting crews to endure whatever discomfort resulted. The psychological impact of these discoveries on Japanese engineers and officers is difficult to document directly, as few left detailed personal accounts of their reactions, but the pattern of their subsequent work reveals the effect. Engineers who had been confident in Japanese design approaches became advocates for fundamental changes. Officers who had believed in the superiority of Japanese warrior spirit began requesting better equipment. The gap between what they learned from captured American equipment and what Japanese industry could actually produce became a source of frustration and, increasingly, despair. Major Saburo Hayashi, assigned to the Army Technical Bureau in Tokyo, wrote in a private letter to a colleague in January 1944 that examining captured American equipment had been more demoralizing than battlefield defeats. Defeats could be attributed to tactics, leadership, or circumstances, but the technical inferiority revealed by examining American engineering was systemic and could not be quickly remedied. Japanese industry was already operating at maximum capacity. Fundamental redesigns would take years. The war would be decided long before Japanese tanks could match American capabilities. The institutional response to these technical discoveries followed a predictable pattern. Reports were written documenting American engineering superiority. Recommendations were made for design improvements. Priorities were established for implementing changes. But actual implementation consistently fell short of what technical analysis suggested was necessary. The reasons for this gap between recognition and response were complex and interconnected. Industrial capacity limited what could be produced, regardless of design knowledge. The Japanese aircraft industry, given priority over tank production, consumed most of the nation's aluminum, high-grade steel, and precision manufacturing capacity. Tank production made do with what remained. Organizational culture resisted admitting that fundamental assumptions had been wrong. Japanese military doctrine had long emphasized that superior spirit could overcome material disadvantages. Acknowledging that American equipment was not just quantitatively superior, but qualitatively better in fundamental ways challenged this core belief. Senior officers who had built their careers on this doctrine resisted conclusions that suggested it was wrong. Strategic priorities shifted as Japan's position deteriorated. By 1944, the focus had moved to defending the home islands against invasion. Tank development, never a top priority, became even less important as resources concentrated on aircraft production for kamikaze operations and coastal defense preparations. The improvements that technical analysis suggested should be made to Japanese tanks were simply not implemented in any significant way before the war ended. Yet the knowledge gained from examining captured American equipment did influence Japanese engineering in subtle but important ways. Field modifications to existing tanks incorporated some American design principles where possible. Improved ventilation systems were added to Type 97 tanks to help with heat, though these could not match the effectiveness of liquid cooling. Better instruments and controls were retrofitted to some command tanks. Maintenance procedures were modified based on American practices observed in captured equipment manuals. These incremental improvements could not close the fundamental capability gap, but they represented Japanese engineers' attempts to apply what they had learned within the constraints they faced. More significantly, the experience of examining American engineering affected how Japanese engineers thought about design problems. The focus on crew effectiveness, the emphasis on reliability and maintainability, the willingness to add weight and complexity to improve operational capability. These American principles challenged Japanese assumptions about what constituted good engineering. Some Japanese engineers, like Yamamoto and Nakamura, internalized these lessons and carried them forward into their post-war careers. Others remained convinced that Japanese approaches were theoretically superior, even if practical circumstances prevented their full realization. The broader story of Japanese technical intelligence regarding American equipment extends beyond tanks to aircraft, ships, and weapons. In every domain, Japanese engineers who examined captured American equipment discovered similar patterns. American designs prioritized reliability, maintainability, and crew effectiveness. Manufacturing quality was consistently high. Materials and components were over-engineered with generous safety margins. These characteristics reflected an industrial base with capacity to spare and an engineering culture that valued sustained operational effectiveness over elegant efficiency. Japanese designs, by contrast, reflected an industrial base operating at the limits of its capacity and an engineering culture that valued efficiency, simplicity, and minimum weight. Components were stressed close to their limits. Manufacturing quality varied as factories struggled with material shortages and increasing numbers of inexperienced workers. Crew, comfort, and ease of maintenance were secondary considerations to achieving specified performance with minimum resources. Neither approach was inherently wrong, but they reflected different circumstances and led to different outcomes. American design philosophy worked brilliantly when supported by massive industrial capacity and sophisticated manufacturing capability. Japanese design philosophy had worked adequately when wars were short and equipment demands were limited, but failed under the sustained industrial competition of a long war. The captured Sherman components at Sagami Arsenal were eventually destroyed in American bombing raids in 1945. The technical reports survived, carefully archived, and later captured intact by American occupation forces. These documents provide a window into how Japanese military engineers understood the equipment they were fighting against and the conclusions they drew from their examinations. Reading these reports today, decades later, is a poignant experience. The Japanese engineers who wrote them clearly understood what they were seeing. Their technical analysis was sophisticated and accurate. They correctly identified the design principles underlying American engineering superiority. They made sound recommendations for how Japanese designs should change, but their recommendations could not be implemented. The industrial and organizational systems that would have been required to match American capabilities simply did not exist in wartime Japan, and could not be created quickly enough to affect the war's outcome. Lieutenant Yamamoto's career after his initial examination of the captured Sherman at Munda Point continued to bring him face to face with American engineering superiority. In early 1944, he was assigned to evaluate a captured M3 Stuart light tank recovered from the Marshall Islands. The Stuart, smaller and lighter than the Sherman, provided an interesting comparison to Japanese light tanks, like the Type 95 Hargo. The Stuart weighed approximately 12 tons, close to the Hargo's 7 tons, but mounted a 37mm gun compared to the Hargo's 37mm, a comparable armament in a similar weight class. This suggested that direct comparison might show more similarity than the Sherman examination had revealed. Yamamoto's examination quickly dispelled this hope. The Stuart's liquid-cooled radial engine, though smaller than the Sherman's power plant, still provided 250 horsepower compared to the Hargo's 120 horsepower, more than double the power in a tank weighing less than twice as much. The power-to-weight ratio favored the American tank significantly. More importantly, the Stuart demonstrated the same design philosophy as the Sherman: robust components with generous safety margins, sophisticated cooling and ventilation systems, ergonomic crew stations, high manufacturing quality. The reliability and maintainability advantages that characterized the Sherman were equally present in the smaller Stuart. The lesson was clear. American engineering superiority was not about specific tank models, but about systematic approaches to design and manufacturing that applied across their entire product range. By mid-1944, Yamamoto had examined components from 5 different American tank types, including the Sherman, Stuart, and the new M26 Pershing that was beginning to appear in intelligence reports. Each examination reinforced the same conclusions. American tanks were designed as integrated systems optimized for sustained combat effectiveness. Japanese tanks were designed as collections of components optimized individually for minimum weight and maximum simplicity. The American approach required more industrial capacity and sophisticated manufacturing, but produced tanks that could fight longer, required less maintenance, and kept their crews effective over extended periods. The Japanese approach minimized resource requirements and simplified production, but produced tanks with limited operational endurance and numerous small deficiencies that accumulated to significantly reduce combat effectiveness. In his final technical report before being reassigned away from the front lines, Yamamoto summarized what 3 years of examining American equipment had taught him. The conclusion was stark, and, for a Japanese officer in 1944, professionally dangerous to state explicitly. Japan was not losing the war because of inferior tactics, inadequate training, or insufficient warrior spirit. Japan was losing because American industrial and engineering capabilities exceeded Japanese capabilities by margins too large to overcome through operational excellence. This was not a comfortable conclusion, and Yamamoto was careful to word his report in technically neutral language that avoided explicitly defeatist statements. But the implications were clear to anyone who read the technical details he documented. The human dimension of this story, the individual Japanese engineers and officers who examined American equipment and came to understand the implications, is largely lost to history. Most left no personal accounts. Their private thoughts and reactions went unrecorded or were destroyed. We have their technical reports, careful and professional, documenting what they observed. But the emotional experience of gradually realizing that everything they had been trained to believe about Japanese technological superiority was wrong. That experience is mostly invisible in the historical record. Occasional glimpses appear in the surviving documents, a comment in a report about being amazed by manufacturing quality, a recommendation worded with unusual emphasis, suggesting frustration that previous recommendations had been ignored. A private letter mentioning the psychological difficulty of examining equipment so superior to what Japanese forces possessed. These fragments hint at the larger story of Japanese engineers, confronting uncomfortable truths, but do not fully illuminate it. What we can say with confidence is that Japanese technical intelligence regarding American equipment was generally accurate and sophisticated. Japanese engineers understood what they were seeing. Their analysis correctly identified American advantages and the design principles underlying those advantages. The failure was not in understanding, but in response. The industrial, organizational, and cultural systems that would have been required to match American capabilities could not be created within the time frame the war allowed. This was the larger tragedy that the captured Sherman and its cooling system represented. Japanese engineers discovered the answer to why American tanks never overheated. The answer was clear, technically sound, and implementable. But implementing it required resources, industrial capacity, and time that Japan did not have. Understanding the problem did not enable solving it, and that gap between knowledge and capability ultimately defined Japan's experience throughout the Pacific War. The examination of captured American tanks represented only one dimension of Japanese technical intelligence efforts during the Pacific War. Throughout 1943 and 1944, Japanese engineers examined captured American aircraft, naval equipment, weapons, and vehicles, building a comprehensive picture of American industrial and engineering capabilities. Each examination added detail to an increasingly troubling portrait of an opponent whose technical sophistication exceeded Japanese estimates by dramatic margins. The pattern that emerged across all these examinations was consistent. American equipment prioritized operational reliability over theoretical efficiency, crew effectiveness over minimal design, and sustained performance over elegant simplicity. These priorities reflected industrial capacity so vast that American designers could afford to over-engineer components, use generous safety margins, and add features that improved usability, even at the cost of added weight and complexity. Japanese equipment, by contrast, reflected the constraints of limited industrial capacity and resource scarcity that forced designers to optimize every component to its theoretical limits. In March 1944, a particularly significant intelligence windfall arrived at the Yokosuka Naval Arsenal. American forces had abandoned several vehicles during the fighting on Bougainville, and Japanese troops had managed to recover a complete M4 Sherman, a jeep, and a DUKW amphibious truck before retreating from the area. The three vehicles together provided a cross-section of American military automotive engineering that allowed Japanese analysts to identify common design principles and manufacturing standards across different vehicle types. The Jeep, officially designated the Willys MB, proved especially revealing. As a quarter-ton utility vehicle, it represented the opposite end of the size spectrum from the 30-ton Sherman tank. If American engineering advantages were primarily about scale and resources, the Jeep might show different characteristics than the heavy tank. Instead, examination revealed the same design philosophy implemented at a smaller scale. The engine, a 134 cubic inch four-cylinder producing 60 horsepower, was dramatically overpowered for a vehicle weighing only 2,300 pounds. Japanese engineers calculated that half that power would be adequate for the vehicle's size and mission. The excessive power seemed wasteful until they considered operational implications. The Jeep could carry loads far exceeding its rated capacity, climb steep grades, and operate in difficult terrain that would stop less powerful vehicles. American commanders could use Jeeps for missions far beyond their designed specifications, because the vehicles had power and strength to spare. The Jeep's cooling system, though much smaller than the Sherman's, incorporated the same liquid cooling principles with a radiator, water pump, and thermostat, providing reliable temperature control in all conditions. The electrical system used a 6-volt battery and generator that were oversized for the vehicle's minimal electrical needs, but provided reliable starting and operation. Every component showed the same pattern of generous design, margins, and robust construction. Japanese attempts to produce similar light vehicles had consistently struggled with reliability problems. The Type 95 Kurogane motorcycle car, Japan's closest equivalent to the Jeep, weighed only 1,100 pounds and used a small air-cooled engine producing only 13 horsepower. It was adequate for liaison duties on good roads in moderate climates, but struggled with heavy loads, steep terrain, or tropical conditions. The Kurogane's minimalist design reflected Japanese engineering priorities. Lightweight, simple, fuel-efficient, it represented elegant efficiency. But examining the Jeep revealed that this elegance came at the cost of operational flexibility. The Jeep could do anything, anywhere, under any conditions. The Kurogane required careful deployment within its narrow performance envelope. The DUKW amphibious truck provided even more striking evidence of American engineering sophistication. This vehicle, which could operate on land as a truck or in water as a boat, represented a technical challenge that Japanese engineers had never successfully solved. Japan had developed amphibious tanks, but a truly practical amphibious cargo vehicle had eluded their designers. Examining the DUKW revealed why. The vehicle was not a simple combination of a boat hull and truck components, but a carefully integrated system. The hull was welded steel, watertight, and strong enough to handle wave action while maintaining the structural rigidity needed for road travel. The propeller and rudder system could be engaged or disengaged from the driver's position. A bilge pump system automatically removed water. Tire pressure could be adjusted from inside the cab to optimize traction on different surfaces. The engine, the same 270 cubic inch GMC straight 6 used in standard American trucks, had been marinized with sealed electrical components and protected air intake. The transmission and transfer case incorporated a power takeoff for the propeller. Every system had been adapted for dual environment operation without compromising performance in either domain. The level of integration and the sophistication of the engineering solutions impressed the Japanese examination team. Their report noted that creating such a vehicle required not just good design but extensive testing and refinement. The DUKW represented thousands of hours of engineering development, something only possible with substantial industrial resources and organizational support. Japanese industry, struggling to produce adequate numbers of standard trucks and tanks, could not have diverted the resources needed to develop such a specialized vehicle, even if the engineering knowledge had been available. What particularly struck Japanese analysts was the manufacturing quality visible in all three vehicles. Welds were clean and consistent. Castings showed no visible defects. Machined surfaces were smooth and precisely dimensioned. paint and corrosion protection were thorough. These characteristics indicated manufacturing processes with strict quality control and skilled workers using good equipment. Japanese manufacturing quality, never matching American standards even in peacetime, had deteriorated significantly by 1944. Material shortages forced the use of substitute alloys with inferior properties. Experienced factory workers had been conscripted for military service and replaced with hastily trained recruits. Precision machine tools wore out and could not be replaced. The gap between American and Japanese manufacturing quality, always present, had widened to a chasm by the war's middle years. Lieutenant Commander Jiro Tanaka, a naval engineer assigned to the Yokosuka examination team, wrote in his private diary that examining the American vehicles had been profoundly discouraging. Every component, every weld, every machined surface spoke of an industrial base operating with capacity and capability that Japan could not match. The vehicles were not superior because of secret technologies or brilliant individual innovations. They were superior because they were products of a manufacturing system that could afford to do everything properly. Proper materials, proper processes, proper quality control, proper testing. Japanese manufacturing, pushed beyond its limits, could no longer maintain such standards, even when engineers knew what should be done. The strategic implications of what Japanese engineers were discovering through technical intelligence became increasingly clear as 1944 progressed. American industrial superiority was not just about quantity, though the production numbers were staggering. It was about quality, reliability, maintainability, and the ability to sustain operations over time. A Sherman tank might not be superior to a Japanese tank in any single characteristic measured in isolation, but the Sherman could operate for more hours, required less maintenance, broke down less frequently, could be repaired more quickly, and kept its crew effective longer. Over a campaign lasting weeks or months, these advantages multiplied. One Sherman provided more cumulative combat capability than several Japanese tanks, because it spent more time actually fighting and less time cooling down, being repaired, or waiting for its exhausted crew to recover. This was the insight that Japanese technical intelligence had developed by mid-1944. But translating this insight into institutional response proved impossible. The reports flowed upward through the military bureaucracy, carefully documenting American advantages and recommending responses. But the responses required industrial capacity that did not exist, manufacturing capabilities that could not be quickly developed, and strategic choices that would have required abandoning other essential programs. By late 1944, the character of Japanese technical intelligence efforts began to change. Earlier examinations had been motivated by hope that understanding American technology would enable matching it. Later examinations were motivated more by the need to understand the enemy's capabilities for defensive planning. The tone of reports shifted from recommendations for improvement to assessments of what Japanese forces would face. In December 1944, Japanese intelligence officers on Luzon examined several Sherman tanks that had been disabled in the fighting around Manila. By this point, American forces were using improved Sherman variants, including the M4A3, with a more powerful engine and wet ammunition storage to reduce fire risk. The examination confirmed that American tank design continued to evolve and improve. But the Japanese response was no longer about matching these improvements. It was about developing tactics to defeat tanks that were acknowledged to be superior. The reports from Luzon focused on identifying vulnerabilities. The Sherman's armor, though thicker than Japanese tanks, could still be penetrated by the Type 147mm anti-tank gun at close range from the sides or rear. The tracks remained vulnerable to mines and obstacles. Close assault teams with magnetic mines or satchel charges could disable the tanks if they could get close enough. These were the tactics of an army that had given up trying to match its opponent's equipment and was instead seeking ways to fight, and effectively despite inferior tools. The final months of the war brought Japanese engineers face-to-face with American equipment in circumstances far removed from the careful technical examinations of earlier years. As American forces approached the home islands, captured equipment examinations became hasty affairs, conducted under air attack with minimal resources. The focus shifted entirely to immediate tactical intelligence. What weapons could penetrate this tank? What vulnerabilities could be exploited? The broader questions about industrial philosophy and engineering approaches became irrelevant as Japan faced imminent invasion. Captain Yamamoto, who had conducted the first detailed examination of a Sherman's cooling system back in 1943, spent the final months of the war at a testing facility in Hokkaido, far from the fighting. His assignment was to evaluate proposals for new weapons that might defend against American tanks during the anticipated invasion. The proposals reflected Japan's desperation: suicide anti-tank attackers carrying explosive charges, buried aircraft bombs to be detonated when tanks passed overhead, bamboo spears for civilian militia to attack tank vision ports. These were not serious military solutions, but the expedients of a nation that had run out of industrial capacity and was preparing to resist with whatever means remained. Yamamoto's diary entries from this period, recovered after his death in the 1980s, expressed his private thoughts about the trajectory from his careful technical examination of the Sherman in 1943 to the desperate proposals he evaluated in 1945. He had understood since that first examination that Japan faced an opponent with industrial and engineering capabilities too great to overcome. The following 2 years had only confirmed and deepened that understanding. Now, Japan was preparing to fight with bamboo spears against an enemy whose tanks incorporated engineering sophistication that represented the full power of American industrial civilization. When Japan surrendered in August 1945, Yamamoto felt not just relief that the killing would end, but a measure of vindication. His technical reports had been correct. The conclusions he had drawn from examining American equipment had accurately predicted the war's outcome. Japan had been fighting an industrial and engineering competition it could not win. Recognizing this truth earlier would not have changed the outcome, but might have saved lives by encouraging earlier surrender. In the immediate post-war period, American technical intelligence teams fanned out across Japan, examining Japanese equipment and interviewing Japanese engineers. The interaction between American and Japanese engineers during this period was complex and often surprising. American teams expected to find crude, primitive Japanese technology. Instead, they found sophisticated designs, implemented with limited resources. Japanese engineers had accomplished remarkable things given their constraints. The Type 97 tank, though inferior to the Sherman, was a competent design that represented intelligent choices within severe limitations. Japanese engineers, for their part, finally had the opportunity to examine American equipment openly and thoroughly, without the pressure of wartime urgency. Many requested permission to visit American factories to see the manufacturing processes that had produced the equipment they had been fighting against. These visits had profound effects on post-war Japanese industrial development. The lessons learned from examining American equipment during the war, combined with direct observation of American manufacturing methods after the war, shaped Japanese industrial strategy during Reconstruction. The emphasis on quality control, the use of statistical methods to ensure consistency, the integration of manufacturing considerations into design processes. These American practices were studied, adapted, and eventually implemented in Japanese factories. By the 1960s and 70s, Japanese manufacturing would become renowned for quality and reliability, the characteristics that Japanese engineers had first observed in captured American equipment during the Pacific War. The story of Japanese engineers examining American tanks thus extends beyond the immediate wartime context. It represents a transfer of knowledge and understanding that would eventually contribute to Japan's post-war economic success. The industrial and engineering capabilities that had seemed impossibly advanced when encountered in captured Sherman tanks became targets to match and eventually exceed in the competitive but peaceful environment of post-war global commerce. Lieutenant Yamamoto's post-war career exemplified this trajectory. After working briefly with American occupation forces, he joined Toyota Motor Corporation in 1947. His experience examining American vehicles during the war gave him credibility and insight into manufacturing methods that Japanese industry needed to adopt. He became an advocate for quality control systems, reliability engineering, and design processes that considered manufacturing and maintenance from the beginning rather than as afterthoughts. The Toyota production system that emerged in the 1950s incorporated many principles that Yamamoto and engineers like him had first observed in American military equipment. The emphasis on eliminating waste, ensuring consistent quality, designing for manufacturability, and maintaining equipment reliability all reflected lessons learned from examining why American tanks, trucks, and other vehicles had performed so effectively during the war. By the 1970s, Japanese automobiles were gaining reputation for quality and reliability that exceeded American products. This represented a remarkable reversal from the wartime situation, and it had been accomplished in part by engineers who remembered examining American equipment during the war and understanding what made it effective. The cooling system that Yamamoto had first examined in that captured Sherman in 1943 became, in a sense, a template for understanding how to design and manufacture products that would work reliably over time. The principles were not complicated. Use adequate materials with appropriate safety margins. Design systems to work together effectively. Manufacture to consistent quality standards. Test thoroughly and refine based on results. These principles, clearly evident in American wartime equipment, became foundations of Japanese post-war industrial practice. The wartime story of Japanese engineers examining American equipment thus connects to the larger story of industrial development and knowledge transfer. Military technology often drives industrial advancement, and the insights gained from studying an instilled opponent's equipment can have lasting effects beyond the immediate conflict. The Japanese engineers who examined American tanks, trucks, aircraft, and ships during the Pacific War were documenting more than technical specifications. They were learning industrial and engineering philosophy that would shape their work for decades to come. Today, over 80 years after that first Sherman was examined in the jungles of New Georgia, the technical reports written by Japanese engineers during the war remain valuable historical documents. They provide detailed information about American equipment from a unique perspective. More importantly, they illuminate the process of technological learning and the transfer of industrial knowledge between competing nations. The reports document not just what American equipment was, but how Japanese engineers understood it and what conclusions they drew. Reading these reports reveals the gradual dawning of understanding as Japanese engineers examined piece after piece of American equipment and recognized patterns. The over-engineered components, the generous safety margins, the emphasis on crew effectiveness, the sophisticated integration of systems. These characteristics appeared consistently across all types of American military equipment, from individual weapons to large ships. They represented a design philosophy rooted in industrial abundance and organizational sophistication that Japanese engineers came to understand but could not match within their resource constraints during the war. The captured Sherman and its cooling system that Japanese engineers examined so carefully was thus both a specific technical puzzle and a symbol of larger truths about industrial competition and engineering philosophy. The answer to why it never overheated was straightforward from a technical standpoint. American designers had created a sophisticated liquid cooling system with adequate capacity and multiple redundancies. But the deeper answer involved industrial capacity, manufacturing quality, design philosophy, and organizational culture. These factors determined not just how cooling systems were designed, but how every aspect of military equipment was approached. Understanding this deeper answer did not enable Japanese engineers to immediately replicate American capabilities, but it did provide knowledge that would eventually contribute to Japan's post-war industrial success. The human cost of the industrial and technical competition documented in these engineering reports was immense. Hundreds of thousands died in battles where equipment advantages played significant roles. Japanese tank crews suffered in vehicles that overheated and broke down while facing American tanks that operated reliably. Japanese soldiers fought without adequate support equipment, while American forces deployed vehicles and machinery for every task. The technical reports, with their careful measurements and dispassionate analysis, describing hardware and systems. But behind every technical advantage documented in those reports were lives affected and outcomes determined. The Japanese engineers who wrote these reports were not just analyzing equipment, they were documenting the tools that were determining the war's outcome and, by extension, affecting countless lives. This human dimension gives the technical story its weight and significance. The cooling system in a tank matters because it affects whether crews can fight effectively and survive. The reliability of equipment matters because it determines whether supplies arrive, whether wounded are evacuated, whether positions can be defended. Technical superiority translates into operational advantages that ultimately save or cost lives. The Japanese engineers examining American equipment understood they were analyzing not just interesting technical solutions, but the material basis of military effectiveness that was determining the war's course. Their reports, carefully documenting American advantages they could not match, were in a sense documenting the reasons for their nation's defeat. This must have been a profoundly difficult truth to confront and record, but they did so with professional competence and accuracy that makes their reports valuable historical sources decades later. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.